Hello, everybody. Welcome to what is essentially our last class for this course, which is extremely exciting, I think. So I'm not going to waffle too much during this introduction session. What we're going to be doing today is looking at a complex circuit or a circuit with lots of elements. And then we will create the said circuit in the schematic version. We'll create a custom component, in this case, a microcontroller. And then we'll create a PCB, finish that PCB design, also taking into account the design mistakes that I made with this specific board. We'll just have a look at how we should do it properly and how we should think about connecting everything. And that's basically it. So we have this again, our Thursday class, we have 2 time slots, but the 2 time slots are spaced in between with I think an hour and a half or something break in between. But as always, I'll keep the session open. Just log in and out as you see fit. I'll leave the session, but then I'll come back in at the correct time, and then we'll continue on. So today what we're going to be doing is looking at a more complex design. It's not that complex. I mean, once you can design a circuit board, complexity is a little bit more difficult. If you've got a good understanding how to create a circuit in the schematic view, and then in the creating a PCB, it's not straightforward, but it's okay. And then we'll do this during this time slot and also during the next time slot. And what we will then also do is in the later time slot, we'll also speak about the exam project and how everything is going to be working through that. And then we'll also do a quick recap of everything that we've done so far and everything that I would expect you to do if you have paid attention during this course. Right, so let's start. I found a Arduino-based project that I would like to do. Now it is a relatively good learning project where you have these Arduino boards. I have one. Sorry for the delay. Like this. So Arduino is the make of the that specific board. It's the company that makes these boards. And what they basically do is they have a microcontroller in the middle, and they have all of these connectors which you can use. And it's also got a programming chip on there and also a couple of other elements like clocks and power management and stuff like that. And you can buy these, they're quite cheap, but a lot of the times you can also try and make your own. So we call these development boards. So they're based around a microcontroller, which you can program, and then you just make all of the inputs and outputs more accessible by adding in connectors, which you can then connect, and also like power connectors, so you can power your circuit. I mean, I do this, I don't do that often, but it's a good exercise in PCB design to create your own development board. And if you have a custom project where you want to use one of these, you can make your own. So a lot of the times we make custom development boards. This is also a prototyping stage where you use a development board to prototype your circuit and see if it works. But then when you create your eventual product, your product probably won't include a development board. So then you will then design your own board, but only with the things or the peripherals that you require. So this one has got, what I think, 48 inputs and outputs. Your project might not need it. You probably only need a 10 inputs and outputs, for instance. So then you design your board only for 10 inputs and outputs, and then you embed that into your project or into your product. So that's what we're going to be doing now. I'm going to be sharing my screen. And once again, if anything happens, if you lose audio or video, or I forget my screen and you're just looking at me typing and moving my mouse and talking about something you cannot see, just let me know in the comment, well, in the chat, like I'm doing here. There are problems. Or send me an email, or however you wish to contact me if there are any problems. Right, I'm sharing my screen. And this is obviously my Eagle landing page. Now, the project that I would like to do is this project. It is, I'll place the link inside the chat so you can have a look at it as well if it's something you would like to practice. But there are lots of different ways, a lot of different projects like this. I just found this one because it's got a really nice circuit attached to it. So it's straightforward. I mean, the project's almost like 10 years old. And it is based around this microcontroller, the Atmega 328. And it gives you a nice list of the hardware that they use. Atmega 328, our power regulating IC. It's got a crystal to clock the microcontroller, a button, couple of LEDs, capacitors, resistors, a pin header, an IC socket, which I also use, which is the socket for the microcontroller to fit into, and the AVR pocket programmer. Well, if you want to program it, but we don't care about that. This is what it looks like on a breadboard. Now we're going to be, and this is what the schematic looks like. Just talking about the schematic quickly, here we have our power input or our power sort of delivery, and that is with a 9-volt battery. This is here, the 9-volt battery like I also used. Going through a power regulation circuit. And then we have what is this? A pull-up resistor connected to the reset. And we have the clock in a certain configuration. And then we have a LED through a resistor here, and some connectors connected to our circuit. And what I really like about this is that this is a circuit that is done through Eagle. So we will be using this going through Eagle. Now, if we look at Eagle, let's just open up a schematic. I just want to show you something. So let's have a look. My libraries are loading. So it cannot find Atmega 328, but I'm relatively sure it has Atmel. Atmega 328. Or something like this. So, right. So let's say the example is now somewhere is the correct microcontroller, but I am not exactly using, because as you can see, there are quite a number of microcontrollers. And this happens quite a lot. You have got a certain microcontroller and you cannot find the exact right package schematic and matching footprint. So then you decide, well, let's just make my own, because it is sometimes a little bit easier or sometimes a bit quicker for that instance. Right, so let's just actually close this. So what we are going to be looking at is this Atmega 328P controller. This is what we're going to be using. And if you scroll down here, we have a couple of data sheets. I've downloaded this data sheet. And if you're looking for this, just Google Atmega 328P. And it gives me this data sheet. It's a relatively extensive data sheet, around about 653 pages, but we're not interested in most of it. No, it does give you a quick overview of what this does. We don't care for now. Looking through the directories, what we are looking for is the mechanical connection or the package overview, what packages they come in. And it's usually at the end, package information. Let's have a look there. So now we have package information. So we have this surface mount configuration. That is not something I'm interested in. So let's see what other configurations they have. I don't like surface mount. Let's see if they've got a through-hole one. And aha, there we have. Dual inline skinny plastic SP 300mm body, SPIDIP. So this is the SPDIP package, which is skinny plastic dual inline package. So let's say this is the component that we have received. So what we are going to be using is I'm using this mechanical footprint to create my my microcontroller, and then I'll use the pin designations from the Eagle circuit that they have provided for us, and then create this circuit really quickly. Well, not quickly, I'll take my time, and but it does go really quickly once you understand what you're doing. So we're going to be looking at this. As we understand, or as we know, there are roughly two things that are very, very important. That is the distance between the pins, and this is this E value, and we can see it is in inches. So as I spoke before, if they give you the dimensions in inches, just stick to inches. It does not matter. It does not make sense for me to now convert this to millimeters or moles or whatever. If I have inches, then I use inches. Like I said, a lot of data sheets give you millimeters or whatever. Whatever they give you is what you work with. Do not waste time converting from inches to millimeters. More often than not, you will make some mistakes. And even if a component is out by a fraction of a millimeter, it might not fit like you would expect. Right, so let's share this again. And then we have this, and then this distance E between the pins. So that is what we are going to be looking at mostly. And this has got 28 pins. So I'm just going to move this over. We go to our open library. And we go to the library that we have created. Let's start with the footprint. And we call this the Atmega 328. And the package was the SPDIP skinny plastic dual inline. So we press OK, and it creates it for us. So now we have our grid. So remember, we are working with inches. So let's just go with inches. Yeah, that is fine. Inches, that is also fine. So as we are dealing with a pin array, I would like my through hole pad, and I go with my pad array here. So my base name. Now this is just the first digit of here. So I have P, it'll be P1, 2, 3, 4, 5, 6, 7, 8, but we're going to change that anyways. We want pins left and right. Pad count we said was 28. Start index, let's start it at 1. DX is, I can keep that there. Our DX is this E number here. E nominal, so they give the maximum and minimum. We usually stick with the nominal, which is 0.31. So that is what we are going to be adding in here, 0.31. And dy, make sure I deal with inches. And dy is the distance between the center of the pins. Where is my data sheet? No, I'm messing this up. And this is the E value here. The E value is here, and it is 0.1 inch. 0.1 inch. I do not want to generate the rectangle. It's something I do myself, but please include the name and also include the value. And then click OK. It usually takes a while for it to generate. And here I have my value, so I can just move it around. Click on move, right click, move group, and I move it around my origin. So this is my design now. Now we can give all of the pins their real names. Now to do that, I can use the I can use this data sheet here, because the pins should all be the same. And it should really be the same, 26, 27. Or I use, alternatively, I use my data sheet. For the pin designations. It doesn't really matter that much because I'm going to be mapping the pins anyways. So let's just leave that for the schematic. But what I can do is on the T place, I create my little it's a little bit awkward. Right. So we can have it P1 up until P28. And this is really as far as we need it to go. We can have square pads, or we can have round pads. It is fully up to us. Usually I change the size of I change the shape of the first pin. So I know what the first pin is in terms of my orientation. So I know pin number 1 is round. And right, what else do we need? We can also have a small arc. And that is not what I wanted. No, let's just leave it. I'll just use this as my reference. I'm not going to write the SDPDIP because it's to do with the footprint package. And now we add in this. Now here, we don't really care. I like to work in millimeters, as always. My secondary grid is also millimeters. And now we can have created there or what symbol they are using. So here, let's just zoom in. Brilliant. We can see it's got a box, pins on the one side, pins on the other side, with the name at Mega 1638 and IC1, but those will be the name and value. So we will then just create this box and then attach pins to it. Relatively straightforward. So we start with, we're working on the symbol. Let's draw a box. And we can decide how big we want this box to be. As this is only like the schematic part of it, let's have it 30 mils. And then I can have, I can also have this 30 and then 60. Click on this. So I have my box. Now I can add my pins. Click on pins. So I can use a pin array. I'm not going to do that because the pin array puts the pins on either side. I am thinking I'm going to be using this mostly. I'll place down my pins separately. There's one pin there. 1, 2, 3, and 3. Pin number 9. And ground and VCC. So once again, I'm just following what they have done here. Then I'll go around and customize my pins. I flip my pin around by right clicking. There's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. And then 1, 2, 3, 4, 5, 6, 7, 8. And 8. And then 1, 2, 3, 4, 5, 6. And I've run out of space. Oh no. Doesn't really make that much difference. I just delete it. 1, 2, 3, 4, 5, and I need a further 6. And I've got 28 pins. Perfect. So I just finish off this line. Now, what I should do as well, I group the pins or group everything that I've done. I would like to move everything. Where am I moving it to? I'm moving it right over my center. As we spoke about, we like having everything around our center because that is where everything is, where we design around. So everything around the center. So when somebody clicks, they just have to click on the center and it selects this. Now we have to customize our pins and give them names. So we are going to give them these names, pin number, and also names. So let's do this. Pin name EC6. And it is also the reset. Let's just apply this. And so I've gave it this dot, meaning it's inverted, just like they've shown me there. Continuing on. This is also a ground pin. This pin is a ref pin. This pin is AVCC. This pin is EB6 XTAL / TOSC1. So this is to do with clocking. The same with this pin, EB7 XTAL2. I've missed something there. And then TOSC2. I've messed up with this a little bit. It should be a 1. We have another GND. So we have GND. GND pin number 6. Number 6. And then this is VCC. I'll just change this GND to pin number 22. And now you might see, okay, well, we have a little bit of trouble here. So what we can do is select these pins. We click on move, just move them over a little bit. Move this line over as well. So now we've got more space here, and we continue naming our pins. This is PCO ADC 0. PCO 1. Yes. We have to do this for all of these, unfortunately. But it is something that, believe it or not, saves you a lot of time and heartache, because now I definitely know that these pins definitely match. PC4, ADC 4/SDA. And PC5, ADC 5/SCL. EDO, RXD, 1, TXD, EO, TXD, ED2, INT0 or interrupt, ED3, INT1, PD4, XCK/T0, PD5, T1, six, seven, AIN1, EB0, ICP, BB1, O, A, nearly done. BB2, this is OC1B, and we have PB3, MOS, OC2, PB4, ESO, PB5 secant. And that's everything named. Next thing we need is the name. To have this capital. And we have it on the names layer. And this one we can have values on the value layer. Right, so that is that. Save it. Open up our class here, and now we can create a new component, and we call it our @mega 328. Call it our through-hole component. Click OK. Yes, create our new component and add in our schematic. We would like this schematic. Place it roughly in the middle. New local package. The only one that can fit is this package. We click on OK, and now we need to connect the pins. So pin number 1 is P6. So now we have to reference these pin 1 to the correct name there. So I'll just go around the left side. Ground 22 is pin number 22. Which other one did I mark? Ground 6 is pin number 6. A ref is pin number 21. A VCC is pin number 20. PB6 is pin number 9. PB7 is pin number 10. We already connected our ground. I made a mistake, actually. Ground 6 is not at 6, actually at 8. I'll have to correct that later on. And VCC is number 7. .80 is pin number 23. PC1 is pin number 24. PC2, pin number 25. PC3, pin number 26. PC4, pin number 27. And PC5, pin number 28. PDORXD, pin number 2. PDOTXD, pin number 3. PD2, pin number 4. PD3, pin number 5. PD4, pin number 6. PD5, pin number 11. PD6, pin number 12. And pin number 13. And then PB0, pin number 14, PB1, 15, 2, 16, 3, 17, 4, 18, and 19. And click connect. Perfect. Let's write a description. The Atmega 328P. Click OK and save it. So that was a lot of work, granted, yes, but now we have created our own custom part and we can use this custom part. Usually you would then, and you know exactly that it fits the one that you have. I do this actually for most of the equipment that I have. So a lot of the times, the standard Eagle designs don't quite fit exactly how I'd like it. So I end up creating my own things in terms of this. So that's what I tend to do a lot of the time. So let's start our circuit. So we have created all of this. Perfect. Let's create our new schematic design. I like to work in millimeters whenever I can. And right, the first thing, I have to put. And then the next thing we do is we add our wonderful frame. And place it at the center. We can, just because we can then just also give the frame a name and a value, just because on the error check, it will give me a definite error. So let's start from this side, moving through from left to right, adding in our components. So we can start with the power delivery. Delivery, it has got a capacitor. Let's see, they've got a capacitor there, a non-polarized capacitor there, 220 ohm resistor and an LED. And we have this power delivery chip, which we saw was the LM7805 IC, which we did use in the past. So let's create these elements. So we also have a diode. And the diode, it's not mentioned, but it's definitely not an LED. So let's have a look and see what we can find. It is an IN404 diode. Click OK, and we add it there. We also need a connector. Now I have a custom connector which I created, which I really like, and it's also the one that I have used in my previous design. We'll work this around somehow. Yes, we will do this. No problem. Okay, diode, we need two capacitors. 2 picofarad capacitors, which are really, really small. And those are the ones that we have RCL. Let's deal with right. Do I want, let's see if I can find a through hole one. polarized EU. Yes. Ah, there we go. So I like this capacitor. Let's enter this capacitor. Let's give it a value. It is our 22 picofarad capacitor. 22 picofarads. And I need two of them, so I'm going to be copying this one. So I have two of these, and then I need a normal capacitor. Well, not normal, it's not polarized. And we see which ones we like. Most of the times you just look for a specific value. I mean, the more you use this, the more you get comfortable with these little designs. And I think I was actually correct with these ones here. With these capacitors here. We also have two of them, but let me just look at the value. 0.1 microfarads. And then copy this. Also need a resistor. A resistor. Let's go for, let's take the American ones. And I like the look of this resistor. I need an LED. A normal 5 mil LED. And then I need the power chip, or the power converter, which is the LM7805. (7805). This is the one that I've used, so I like this one. I know how it works, and I'll place it down. Right, so let's just go and have a little break. I feel like run over my usual break time, so let's just take a 5-minute break, and then we'll continue on adding in the components. Right, see you in 5 minutes. Hi, welcome back. So I've been looking over what I've done so far and the design, and I've made a couple of mistakes. They're not so major. I just misread one of the components values, which I'll show you. So I'm zooming in on this, and here I see that's 10 microfarads, and this is 0.1 microfarads. So these has to be switched around. It's not that much of a big deal. We can quite easily change it. Let's have this as it's not a picofarad, it is 10 microfarads. And these ones are by 0.1 microfarads. Right. 10 and microfarads. The next thing that we need is we probably need a VCC connector and a couple of grounds, but let's just connect this up as it is in this way here. Then we'll add in our ground connectors and so on and so forth. Right, so our connector ground, or the power, incoming power, runs from there to the diode. It gets filtered by this component. Let's just move this a little bit out of the way there. And also another capacitor here. We have our IC here. And then on the other side, we also have another filtering capacitor here. This capacitor here as well. And this running into an LED here. So we can connect this up, ground running to there, the diode running into this element here, making sure these are all connected. Right. What we now also need is our VCC connector. That's the one we would like. And we connect VCC to here. Yes, merge that net into VCC and also have a ground connector. We have our ground connector. That, and also flip this around. That is also ground. And we make this whole connection here ground. And now we've done our power delivery circuit. Just a quick word on that. I mean, all circuits have some sort of power delivery, power circuit, and this is no different. What this circuit is consisting of is a regulator and then a couple of capacitors to smooth out the power source. Why does it need that smoothing? Because if you think in terms of noise, we spoke about noise, it is unwanted signals and fluctuations in voltage levels that a power source like a battery might have. So we usually have this power conditioning circuit stepping up or stepping down the voltage, in this case, stepping down from 9 volts to 5 volts, and then having a couple of filtering capacitors to further filter out the signal so that we have a nice and steady 5 volts going into our controller. Because these microcontrollers like to have a very steady stream, a very steady, nice looking 5 volts without fluctuations in it. So we have some sort of power delivery circuit usually attached to this. This is where this comes in as well. The power delivery in this case are these two capacitors up there. And then also it's got a series of diodes and also a regulator. And that's also what we're doing for our circuit here, in case you were wondering what that circuit is. Now, the next thing we can do is let's drag in our controller and then start connecting up our controller. Let's just zoom out a little bit. Let's have a look at clear our search. Where is there we have it. And we can click it down there. And as you can see, the name changes and also the value also changes. Perfect. Now we can do the first connection. We need another resistor. Oh, firstly, let's give that resistor a value that doesn't feel out. It is 220 ohms. Here we need another resistor. We see we use this resistor. So it's good using this because now we know that all the resistors that we are using deal with the same or has the same package. So that we don't have different resistors with different package types. So now we are creating a pull-up resistor for a, remember we had the pull-up, pull-down resistors. Now we also have a button which activates a reset. So we need a push button. Let's see if this finds anything. Adafruit has got a push button. And I like the look of this push button switch. We have it connected there. This should be around about 10,000 ohms. We have our VCC connector on the one side. Oh, I don't need that. Click on this little arrow. There's a little downward facing there. We have our VCC connector and also our ground connector. Now we can connect up everything. Connections, 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 and our switch going in there. Perfect. We then need another ground connector for here. So you might say, oh, well, just connect it to there. We don't know how busy our schematic will get. So let's just have its own ground connector there. You can move around the ground there. Connect that up. A ref goes to an AVCC goes to VCC. So we have a VCC connector. Let's have it like this. And then we connect these up like that. The next element that we need to do is we need to have two capacitors and also these, the specific crystal. Now, what does that crystal do? Well, that crystal is an external clock. A lot of microcontrollers, they do have the ability to clock themselves. I give the frequency, the operating frequency of that it uses, but a lot of the times, almost all microcontrollers have got an external clock, and that is that element right up there. So for a lot of microcontrollers, we would have an external clock, and this one, our design is no different. It's just a better, more, what's the word I'm looking for? A more reliable clocking source. So that gives the frequency at which our device executes. So let's have a look and see if we can find that specific part. No. Crystal, there we go. And let's see if we can find a specific crystal that would work for our device. That, I think, looks roughly correct. Now we just have to find a crystal that would work. This is one that I have worked with. This specific footprint is one that I know does work. And we also need now two capacitors. These two capacitors. And these now are my 22 picofarad capacitor. And once again, I think these are also filtering capacitors for my 16 megahertz clock. So how this circuit now works, let's just rearrange everything so it's a little bit nicer. Our circuit runs from PV6 to over there. We then have our, this away, our clock. Move this a little bit down so we have space to connect. Next there, and it also connects down to there. Let's move this a little bit so it makes it a little bit neater. Okay. And then referring back to our schematic, it is now connected to this ground connection. We get another ground connector for us, or a ground net connector. Uh, Connected, and now I need a VCC connector. Oop. And that is my left side basically done. So now what we need to do is we need to connect the right side, which is basically just these connectors here. So we have 8-pin SL3 connectors. So let's see which pins I like. Don't like these connectors that much. I like the SIL connectors a lot. So as you get more experience, you will find out which connectors you like. I know which connectors I do like. And the connectors that this design use are, I don't really like because they are very proprietary. The SIL connectors that I like more are more these types of connectors. We can just simply stick in a wire and it works. But as you get more experience, you have more experience with different types of connectors, and you will find which connectors you use more. For my personal experience, I like the SIL type connectors a little bit more. So let's get that going. So let's find out which connectors I am going to be using. Let's look at SIL type connectors, resistor SIL, I don't want that. And that does not work. Let's have a look at connectors. So all these CON are actually connectors. Now there are so many different types of connectors that you can't really go through all of them. Let's just see a search on it so we can have a better idea of what we are looking for. 1x4 pins. This is also an Arduino, but we don't want that. Well, these connectors, nope, definitely not these types of connectors. 4 amps, no, not these connectors. These might actually work. Let's see what else we have. You see, we've got so many different types of connectors. It usually is a very, very, very hard way, or you'll spend so much time looking through connectors, and then you find your favorite ones, and you pretty much stick to that type of connector. Molex connectors also very, very useful, but it's a proprietary connector, meaning that you have to buy that specific connector. These connectors, not so nice. And I usually end up scrolling through all of these different types of connectors and then going back to the ones I originally saw first. So let's say, right, we are having trouble selecting a specific connector. Let's find, oh no, not this one. No, not these Molex connectors. Definitely not these ones. Right. So as almost always, I end up with just choosing meter fruit, 555, 1 times 17. I actually like these. Right, let's take these ones. This is a pin header, meaning they've got these equally spaced pins, and I can use them quite easily, and I can buy them quite easily from this company. I have 1, 2, and 3. Great, sorted. Now I can connect up my elements. So here I'm needing a VCC connection and also a ground connection. Pin number 1 is connected to VCC, and this pin number 2 is connected to ground. Why are those 2 pins external going to VCC and ground? Well, if you're building a circuit for a development board like this, you might need to power those components. So you then share the VCC or the 5-volt output of your circuit and also the ground. So then you can connect LEDs and sensors and all that kind of stuff directly to your circuit. Let's move this, group this, and move this a little bit like so, and then connect these up. Right. Now these are straight connected directly to that. Perfect. That's exactly what we're going to be doing. So it's not wanted. And last but not least, we have to connect up this side. And we also need a resistor and an LED and a ground connection. So let's just connect this up first, move it into place. Actually, there is a 5 connector. So this is not 8. We don't need the 8. I made a mistake. Let's delete this connector. So these are 8. That's 8. That's a 5-pin. So let's get a 5-pin connector. Pin header. Oh, we don't have a 5-pin. Oh, no. That is not great. 1 by 9, 1 by 10. So what do we do? Well, let's just use a 6-pin connector. And then we just don't have one of those connected, which is fine. Let's connect this up. And then we need another LED. So we can just copy this LED here with its resistor there, because it does the same thing. And also we need a ground connection. I'm pretty sure it's going to moan about the LED not having a value. So let's have this as a green LED. And this one as a red LED, because why not? So this is now our whole design scheme out. So what is the next thing that we should do? Well, obviously we save this and save this as our Arduino dev. Now I should really have been saving that more, but I honestly forgot. So let's see what we have. We have missing junction. Aha, right. Let's fix that. Let's zoom in, delete this, and make sure that this does make good contact. Missing junction there. Okay. Let's delete this as well. And just make sure that the connection is well done. Power pin connected to power connector. That is fine. Now we have all of our parts, these have got no names. Okay, let's give them values. Value for this. Header 1. Header 2. And this is header, let's keep this 3. And it will probably also tell us something about the switch. SW1. Let's have a look. No errors, 1 approved warning. And we are done. Well, we're not done just yet. We need to name all of our nets, right? That makes it everything easier. So let's have a look and see. This is ground. That should be power. That is diode to regulator. This is VCC. Let's have this as R1 to LED1. That should be ground. This should be reset. This is obviously ground. This is CLK. This is the CLK2. Ground. PCO0, PCO1, PC, oh, this is actually PC2, PC1, PC2, PC3, PC4, and PC5, ED0, ED1, ED2, 3, ED4, ED5, ED6, ED7, EB0, EB1, two, EB3, EB4, EB5, this is R3 to diode, oh no, LED 2. Right, so that should be all of our nets named. Let's save it again. Okay, so we're reaching the end of this class, but that is basically our schematic done. In the next class, which starts at, let me just check and make sure we are all on the same page. I just want to make sure that I do not lie to anybody. Nope. Next class starts at 1900 hours for you guys. So right, then we'll continue on with this design, taking it to PCB, and then making everything nice and neat and creating a good PCB and our own development board. Right, as I said, I'm just going to be logging out when the time is right, and then we will continue on finishing this design and then also speaking about the exam later on. Right, have a good, nice long break now, and then I'll see you in the later session. Bye.